Welcome to the lecture series of digital electronics in sequential circuit. Today we'll discuss the timing signal, how it can be helpful and why it is required to control any system. So remember that thing, the sequence of operation in digital system are specified by the control unit, and the control unit supervise the operation of digital system. A big digital system is that it gives the some signals to the arithmetic unit or logical unit or memory unit. So it is required to generate the control signal, and this control signal is depends on the width or operation timing is required. The timing sequence in control unit can be easily generated by the means of counter or shift register. So counter or shift register is useful to generate the timing signal. Let's take one example. Suppose we design the timing signal of word time generation. And here word time generation, word we know that the 8 bit is that. So that means we use the 3-bit counter here. 2 raised to 3, 8 pulses will be generated. At clock pulse, it will become 1, 1, 1. Initially, it will become 0, 0, 0 to require 8 pulse, and then the stop is 1. Else, stop is always 0. Okay, so now how it can be? Assume that the word time generate must be a period of 8 clock pulse, as shown in this figure. We know that the start signal will set the flip flop queue. Start signal, we set the flip flop queue. Okay, it will give a set signal in this negative age. So after the setting, the Q output will become set on this clock pulse, and then clock pulse count 1, 2, 3, 4, 5, 6, 7. At that time, it starts from 00 to 001. Here 001, 010, 011, 100, 101, 110, and 111. At that time, the 111, the flip flop gate output is set to 1. Stop equal to 1. So stop equal to 1 after the 8 width pulse. At that time, the Q output, the reset equal to 1 and set equal to 0. Already set is set to 0. Okay. So at that time, between here, the set and reset are equal to 0. So the Qt plus 1 equal to Qt. But at this, after this time, the set equal to 0 and reset equal to 1. So the output is reset. So that means the clock pulse counter 0002 clears, and now it time control signal period of 8 pulse. Also that the stop signal in this circuit can be used as a start of another word control in another circuit, just as a start signal to use in the circuit. So this is can be start of the another circuit. Okay, so in this way the timing signal word pattern is generated. It depends. Suppose I want a 16-bit counter, so it can be count 0002 to 111. So 16 pulse the word time control signal is generated. The in parallel mode operation, a single clock pulse may specify the time at which an operation should be executed. The control unit in a digital system that operates in parallel must generate the timing signal that stay for only one clock pulse period. But these timing signals must be distinct from each other. Timing signal that controls the sequence operation in digital system can be generated by shift register or a counter with decoder, and it is called as a ring counter. Ring counter, there is a two possibility. One is with the counter circuit, and the second possibility is with shift register. Okay, remember that thing. The shift register, counter equal decoder, counter and decoder, and shift register. Two possibilities are there, and it is called as a ring counter because it is in ring fashion. Again, at initial stage will often after the final stage. The single bit is shifted to one flip-flop to the other flip-flop to produce a sequence. Let's see some example. Suppose here this is the circuit, the output is required at initially the 0001, and this one is shifted here. So shifted and counter, both the circuits are required. Suppose this is a shift register. So this one will shift here at the second state to 1, again second to third T2, and then T3, and this again shifted to input side of T0. But initial value is required 1 0 0 0, then it will become shifted 1 0 0. Next state it will become 0 1 0 0, 0 0 1 0, 0 0 1 0 1, and then again from the initial stage. The time this to each flip flop one state every 4 clock pulse and produce one for the 4 timing signal. Okay. Now let's see how it is possible with bit count. So count enable give the one control signal. It start from 0 0. At 0 0 T0 is 1. Counter will increment the one factor 0 1. So T1 is 1. Then next is output of 2 bit is 1 0. So T2 will become 1, and then else is 0. And then 1 1, the T3 will become 1 at this stage. Else the output is 0. So the timing signal will enable the clock pulse will provide the multi-phase clock pulse. Like as T0 is ended with clock pulse, the output of the AND gate will generate the clock pulse and 1/4 of the frequency of the master clock pulse. So master phase clock pulse can be used to control the different register. This is also we can say that it's a frequency divider circuit is also there, which divide the frequency. So to generate the 2 raised to n timing signal, we need either shift register with 2 raised to n flip flop, or okay, 2 raised to n flip flop, or n bit counter with n to 2 raised to n decoder. Two type of the functionality is required. In first case, we need a 16 flip flop. In second case, we need a 4 flip flop and 16 4 input to 1 AND gate decoder side. So it is possible to generate the timing signal with the combination of shift register and decoder. In this way, the number of flip flop is less than a ring counter, and the decoder requires only 2 input gate. This combination is called as a Johnson counter. Okay, Johnson counter. It is a k-bit ring counter. K-bit ring counter is there. Okay, output. So how k-bit is that? On how many flip flops are required? 1, 2, 3, 4, and the number of state can be doubled. The number of, remember that thing. 4 flip flop is there, but it can be count 8 bit. So number a switch tail counter is a circuit which shifts the register with complement output of the last flip flop connected to the input side. Okay. Uh, let's see. This is the figure diagram. It shows the shift register. The circular connection is made from the complement output of the each rightmost flip flop. Okay, complement. This E dash. It is connected to the input side. So last bit QD is the complement of the rightmost flip flop is there. The register shift contains ones to the right every clock pulse, and at the same time, the complement value of the E flip flop is transferred to the A flip flop, starting from the clear state. And the switch tail encounter goes sequence 8 state in general. So AND gate output is required. Remember that thing. So K switch will go to the sequence of 2K state. This is the K bit, but it generates the 2K states are there. Starting from all 0 0 0. Okay, all 0 0 0. Each shift to the insert once from the left hand side. Suppose here the sequence number 1, all 0 zeros are there. 0 0 0 0. E is 1. So the next state, the E is 1 and remaining all 0 0 0, because E is still 0. So E dash is 1. Next state it will become this E, this one will be shift here. So the next state is 1 1 0 0. E dash is 1, so again E dash is 1 here, B is shifted to here, and C will become 1. So next state is 1 1 1 0. E is not changed, it is stable. So again the C is here and E will become 1, but previous value is 1 here. So it will become 111, and now E dash is changed to 0. So now D is equal to 0 in this fifth sequence. Now what happens? This will become reflected to here 0. So it will be 0, 1, 1, 1, 1. Now this 0 is shift to here in the next clock pulse 0, 0, 1, 1. Next clock pulse this will become 0, and the next clock pulse E will become 0. Okay. So now when this is 0, 0, 1, 1, it will become 0, and after that the next sequence will become will become 0 here. Hmm. Now here the question is as how the output can be generated from this thing. So to decoding the k-bit switch tail encounter, we have to 2k sequence follows the regular patterns. All zeros. So here the output ND gate is required. In the first case, the output is A dash E dash. Second case AB dash. So this is the sequence number 1, sequence 2, sequence 3, sequence 4, sequence 5, sequence 6, sequence 7, and sequence 8. Okay. Now let's see. Sequence only sequence number 1 is 1 only in the first case. Okay. A dash E dash is 1 in only the first condition. A dash E dash. Remaining time it will be 0. AB dash is in second state. BC dash is in third state. Okay. A is in second stage, C stage. Similarly, this is happen. Else, these all are remaining 0 in remaining condition. One disadvantage of this circuit is that it finds itself an unused state. It will persist to moving from one invalid state to the another invalid state. So this difficulty can be corrected by modifying the circuits to avoid undesirable conditions. One correcting procedure is to disconnect the flip-flop output from D. This goes to D input flip-flop C. Instead of that thing, the C input, only one is change required, this one here. So DC is equal to, instead of direct, we connect the A plus C into B to remove unused state to used state. Next used state, closest state. So the DC flip-flop functionality of D input flip-flop C is changed. Johnson counter can be constructed for any number of timing sequence. The number of flip-flop needed one half of the number of timing signal. And the number of decoding gates is equal to the number of timing signal. Only 2 input gates are employed. So in this way, we can design the different type of ring counter or Johnson counter. I hope it is making sense. Have a good day.